Welcome back. Section 2-2, Solving Linear Systems. Suppose you are given a system of linear equations, a11 x1, a12 x2, all the way until a1 and xn equals b1. Likewise, a21 x1, a22 x2, all the way until b2, so on. You have m equations in n variables. We know we can write this in the form of a matrix equation. That's your coefficient matrix. You have brought in all the coefficients. That's your variable matrix. It's a column matrix. Equals, that's your result matrix, which is the column matrix, B. AX equals B. That leads us to an augmented matrix. So it's a longer matrix, the last column being the B matrix. Okay. So start with coefficient matrix, draw a straight line, and then the B matrix. Now, the method of elimination to solve the system. This system, the system we just saw, directly translates to row operations on the augmented matrix AB. You see, when you have a system of equations, we are allowed to interchange rows. We are allowed to multiply one equation throughout by some number or divide by some number. We are allowed to take combination of two equations. These are basically elementary row operations. So from one linear system AX equals B, you do these elementary row operations and get a new system CX equals D. If they are row equivalent, then they have the same solutions. That's what this theorem states. Let AX equals B and CX equals D be two linear systems, each of m equations in n unknowns. If the augmented matrices AB and CD are row equivalent, then the linear systems are equivalent. That is, they have exactly the same solutions. I hope you understand the importance of this theorem. It is straightforward, but let's go back to this system. So remember, if I'm given an equation, I am allowed to multiply both sides by some non-zero constant. I am allowed that. I am also allowed to take a combination of these two, right? Add these two and so on and so forth. What else am I allowed? I'm allowed to interchange. Write this row first, that row last. It's the same system. That's all we are saying. So by making these changes, it may look like a different system, but you actually have the same solutions. That's what this theorem states. Suppose you have two systems, AX equals B and CX equals D. Both of them have m equations in n unknowns. Build augmented matrices for AB, augmented matrix CD. They are row equivalent. Means what? We have used row operations. We have maybe interchanged two rows. We have maybe multiplied one row by some number or divided a row by some number, non-zero of course. We have taken a combination of two rows. That's what it means to say row equivalent. So if you do that, well, you still have equivalent systems. That is, you have exactly the same solutions. Proof. The elementary row operations on the augmented matrices are the three manipulation on linear systems. 3 manipulations on linear systems which result equivalent linear systems. We also note that if one system has no solution, then the other system also has no solution. So you see, they have exactly the same solutions. If by doing all these row operations on your equations, you get no solutions at the end, it actually means the original system did not have solutions either. If you find a solution at the end, that's what solves the original system. That's all we are saying here, okay? Nothing very unusual or unexpected. Now, a system is called homogeneous if all the right-hand side numbers, the output numbers are 0. Okay? Written in matrix form, what is a homogeneous system? AX is the 0 column. Corollary. If A and C are row equivalent m by n matrices, so these are, mind you, coefficient matrices, then the homogeneous systems AX equals 0 and CX equals 0 are equivalent. Well, of course, because what is the meaning of row equivalent? You have put in place a sequence of row operations. Maybe you interchanged some rows. Maybe you multiplied a row by some non-zero constant. Maybe you took a combination of 2 rows. Well, eventually, they have the same number of solutions and exactly same solutions. Proof follows from the theorem we just saw. With B equals 0, D equals 0. Now, let's understand the Gaussian elimination method. To solve the linear system AX equals B, we use the following steps. Step 1. Use elementary row operations to transform the augmented matrix AB to CD. What is CD? It must be in row echelon form. Once you have row echelon form, use back substitution. Okay, work backwards to find solution of the entire system. Here is an example. Okay, so only 2 steps. Reduce your augmented matrix to row echelon form and then use back substitution. So here is a linear system. They are specifically telling us to use Gaussian elimination method. You'll see in a few minutes why I emphasize on this. Gaussian elimination method. Okay, so here we are. I want to get a 1 here. Okay, instead of dividing by 3, why don't I interchange row 1 and row 2? Okay, that is the augmented matrix. First step is to interchange row 1 and row 2. Let me remind you, augmented matrix, all you do is bring down your coefficients, bring down these solutions, keep a vertical line between them. Now we are using row 1 interchange row 2. That's what that symbol means. You should be able to write such symbols, okay? This is the short form of saying interchange row 1 and row 2. Notice arrows on both ends. Alright, so you interchange row 1 and row 2, you are here. Now you want to get a 0 here and a 0 here. Keep that in mind. Row 1 times negative 3 gets added to row 2. Row 1 times negative 2 gets added to row 3. Keep that in mind. Row 1 times negative 3 gets added to row 2. That's your new row 2. That's the symbol. That's the symbol for all that we say. Row 1 times negative 2 gets added to row 3. That's your new row 3. Notice the arrow, it's only one-sided arrow. So you have zeros here and all these other numbers change. Okay? All these other numbers change as per whatever we had previously. Okay? You will have to double check. These numbers will change. Okay? say you're multiplying by negative 3, adding to this. Negative 15 plus 2 is negative 13, and so on. All right. Now, everything looks good. You have zeros below the leading one. You want to get a leading one here. So row 2, you're multiplying by negative 1 over 13, calling it new row 2. So that's the symbol for this operation. So you're dividing row 2 by negative 13 and calling that the new row 2. So notice negative 13 divided by negative 13. 16 over negative 13. Negative 13 divided by negative 13. Now you want to get a 0 here. 9 times row 2 plus row 3 is your new row 3. 9 times row 2 plus row 3 is your new row 3. So you have 0 just under 1, and the 1 here got changed. The negative 12 here got changed. Check my work, make sure it's okay. All right. So now you have 0 under 1. Now all you need is 1 at the spot of 11. Dividing row 3 by negative 11. So that's your row echelon form. Notice zeros under 1. Okay. Now you are going to use back substitution. What does that mean? Well, rewrite this if you like with variables back. X plus 5y minus 3z equals 5. 0x plus 1y minus 16 over 13z equals 1. 0x, 0y, 1z equals 3 over 11. So you got z. So this is why we call it back substitution. You got the last variable first. Now you are going to put it here. For y, solve for y. Once you have z and y, put them there and find x. Okay? That's your x. All right? Well, how is Gauss-Jordan reduction method different? First step, you are going to reduce the augmented matrix to the reduced row echelon form. That is, not only do you have zeros below the leading ones, you want zeros above the leading ones as well. Back substitution is not needed. We obtain the solutions, if any, right away. For example, consider the same system we worked on right now. This was the row echelon form. Now you want to make it reduced row echelon form. That is, you want zeros above the leading ones. Start from the last column. Okay, don't start from the middle or the first. Well, there is nothing above, but start from the last column. Starting from the last one. Okay. So you got a 0 here by this operation. Let's go back, remind ourselves. 16 over 3 times row 3 plus row 2 will give me 0 there. Row 3 plus row 2 is your new row 2. All right. Now I want a 0 here. 3 times row 3 plus row 1 is your new row 1. You got 0 there. Notice this number also changed accordingly. Now I want a 0 here. Negative 5 times row 1 plus, negative 5 times row 2 plus row 1 is your new row 1. So I got a 0, 0 here, and this number changed. So you see, directly, no substitution needed. Reduced row echelon form gets you x plus 0y plus 0z, that is x itself, 0x plus y plus 0z, so y itself, you have solved for the system. Okay, let's continue in our next video.